Okay, so mechanics and statics, it's really the study of forces, okay? Mechanics, typically our forces involved with particles undergoing some sort of motion. And statics, our particles are typically stationary or what we would consider to be in equilibrium, all right? Forces, so let's have a look at through sort of basic, I guess, definitions. Forces are vector quantities, so they have magnitude and direction. Okay, and sometimes we resolve forces using a vector field to help us identify, components of forces. All right. Now, my weight force is the force that a particle experiences due to the force of gravity. Okay, so now the unit of force in here, so we're going to call it the kilogram weight. All right. Now, sometimes the kilogram weight is more typically, and I will interchange between the two. In year 12, we tend to work in G newtons. So we're going to work with the kilogram weight as a unit of force. And so that's the unit of force due to gravity of 1 kilogram. Okay. Now, the standard of force is called the Newton. Okay. And 1 Newton, okay, so a mass of m kilograms has a force of m kilogram weights, which is mg newtons. Okay, so typically we might often talk about how a particle of say 5 kilos is experiencing a force of 5 kilogram weight or 5g newtons. Okay, and that's how we might reference it. All right, but this year we're going to work mainly with kilogram weight. All right, now the resultant force is the opposite force that a particle experiences. Okay, so for example, me standing here will be a generous 100 kilogram weight. Okay, so that's the force of gravity acting down on me. Now, if there wasn't a force pushing up the opposite direction, a normal force, well, then I would continue to be moving down. So if a particle is stationary, there is an equal and opposite force also involved. All right, so typically for a 5 kilogram box just resting on the ground, there's a normal force or a reaction force acting from the ground on the box, and then there's the weight force acting of the box on the ground, okay, which is my W kilogram force there, and my N force or my normal force acting vertically up, all right? My normal force always acts perpendicular to the surface. So if I happen to be on a sloping surface, okay, my normal force is not going to be vertically up, it's going to be up acting off on the angle. My weight force will always be vertically down. Okay, so you can see there the weight force is still vertically down. The normal force will be acting perpendicular to the surface. Now, tension force is the force that a string, that's what we call the force that a weight force or a weight of a particle sort of resting on a string, I should say, applies a tension in the string. Okay, so if we have a look in here, we can see a bit of string holding up a block. Okay, and so I have a tension of the block on the string acting vertically up, but I also have a tension of the roof, if you like, on the string acting vertically down. So they're my two weight forces, or they're the two forces in the string. Okay, and assuming that that string is unimpeded, it could be sliding over what we would call a smooth pulley. So if there's no friction and the weight force is allowed to slide freely along the string, and we call it a frictionless or a smooth string, well, then those tension forces will be equal. All right. So if we have a look at a bit of an example here. All right. So in the diagram on the left, if we consider the particle 1, okay, I've got the two kilogram weight. So there's a 2 kilogram weight force acting vertically down, which means there's a tension in the string acting vertically up. All right. There's the same tension of the string acting on the roof. All right. So if we just resolve around this system, I'll put a 1 around that system. Okay, because my particle is stationary, the forces acting up are equal to the forces acting down. So my T1 force acting up is going to be equal to the 2 kilogram weight force acting down. So T1 is equal to 2. All right. As opposed to, let's have a look at the second system. We can see system A here. We're just looking at the forces acting on that particle. All right, because we've got two different particles. So again, I've got a T1 force acting up and a 2 kilogram weight force acting down. So there's my T1 is equal to the 2 kilogram weight. But if I look at particle B, I've got a 2 kilogram force acting up. I've got a 2 kilogram weight force acting down, and I've got a T1 force acting down. So there's the two downward forces. All right, so T2 is actually equal to T1 plus that 2 kilogram weight force. We know from the previous exercise that the T1 force is the 2 kilogram weight. So the tension, T2, in that other string, and it kind of makes sense, doesn't it, is a 4 kilogram weight. So we've got two 2 kilogram weights. So really the total weight of the object acting down is 4 kilograms. So it makes sense that the tension in that string is 4 kilogram weight. All right. If we have multiple forces in play, okay, acting on a point and they're in equilibrium, which means that they're stationary, it means, let's just get rid of that and I'll just redraw that. It means we can draw a triangle of forces. So remember your vectors. If we have a vector where we go off in a vector A to vector B to vector C, if they add to form a triangle, there's a couple of things. One, they're linearly dependent, okay? But more importantly, we're back to our starting point. So the net displacement is 0, all right? So that's similar with our forces. If our particle is stationary, it means that our net forces are 0, which means these three forces can form a triangle. So if I just identify how, there's my green F3 force acting down. In fact, I'm going to extend them slightly. My red F1 force acting in this direction. And my blue F2 force. So don't forget when we add our forces, we add top to tail. So if I put a black dot on the starting point of the forces, there's the start of the F3 force. That's the start of the F1 force there. And that's the start of the F2 force there. All right. Now let's think about where theta 1 is. Theta 1 is the angle of the acting between F1 and F2, in between the red and the blue line. So that's theta 1 there. Yeah. Which means that force in there is 90 minus theta 1. Yeah. If I think about the red theta 2 force, theta 2 is acting between the F3 and the F2, which is this angle here. So the one in there is 90 minus theta 2. And the final one, if we put theta 3, which is acting between the red and the green force, 90 minus theta 3. So if we have a, oh, I've used the wrong colors. Hang on, I'll make that a blue one. So if you consider thinking about that whole triangle and our cosine rule and sine rule, the F2 force, yeah, it's directly opposite the theta 3 angle. Yeah, the F1 force in red is directly opposite its angle, and the F3 force in green is directly opposite its angle. So it has the same properties of what our triangles normally do, and that's important because we're going to apply very shortly I guess a sine rule application, a really tremendous application of the sine rule in here to help us resolve our forces. All right. So practice creating those triangles though with some of these examples here. So a particle of mass 8 kilograms is suspended by two strings attached 2 points in the same horizontal plane. If the two strings make angles of 30 and 40 degrees to the horizontal. All right, so I might just get a completely different color. So there's my 30-degree angle, there's my 40-degree angle, slightly bigger, which obviously from our knowledge of triangles, that's a 110-degree angle inside. So from outside the triangle, they're alternate angles. So that angle there must be 30, this angle here must be 40, all right? So if we now create my triangle of forces, you can see my T2 force acting up in its direction, my green T1 force acting up in that direction there, and my blue 8 kilogram weight force acting vertically down. Now, if we just use our knowledge from what we experienced before, okay, so that angle in here must be 120 degrees. The angle in here is 90 plus 40, which is 130 degrees, and 110. So that 120-degree angle between the yellow and the blue, which makes it 60 inside. And we can get all our angles using the same knowledge. All right. So once we get all of my angles, create my triangle of forces, okay, I can use my sine rule knowledge to say that T1 over sine 60 equals T2 over sine 50 equals 8 over sine 70. So that's my sine rule. And from there, we've got my 8 over sine 70. So then I can just manipulate, multiply sine 60 across to get up 7.37 kilogram weight, multiply the sine 50 across to end up with 6.52 kilogram weight. So they're the tensions in the respective strings. And as you might expect, the T1, because it's acting a little bit more vertical, the tension in that string is a little bit greater, yeah, because it's acting more up and down. The angle's slightly different. All right, let's have a look at another one. A particle of mass 15 is suspended vertically from a point by a string. The particle is pulled horizontally by a force F kilogram weight so that the string makes an angle of 30 degrees. Okay, so there's my 30 degrees to the wall. So there's my 30 degrees, which means that's also 30 degrees. Tension in the string, the 15 kilogram weight force in green acting vertically down, the F kilogram weight force acting horizontal. So again, I create my triangle of forces. You can see that we actually create a right angle triangle where that angle in here between yellow and green is that angle here between yellow and green, which is 30 degrees. So we can just use SOHCAHTOA there. Okay, or look, we could use the sine rule as well, but it's a right angle triangle, so we just use SOHCAHTOA. So tan of 30 degrees is opposite over adjacent. So F is equal to 15 tan 30. I've got the hypotenuse there, and I've got the adjacent. So cos of 30 is 15 over t. So t is 15 on cos 30. All right. So once we get that triangle, if we've got a right angle triangle, we can use SOHCAHTOA. If we don't, we can use a cosine rule or typically a sine rule, to be honest. Example 4, last one. All right, so again, here's my particle. Okay, a mass of 20 kilogram weights on an inclined plane. And again, we're just going to create my triangle of forces. So you can see that red Newton force there is perpendicular to the plane, and the force F is horizontal to the plane. So therefore, they're at right angles, aren't they? So there's that right angle there. And then my 20 kilogram weight acting vertically down is over here in green. All right. That 30 degree angle, if we think about extending that normal down there, there's my weight there. So if I consider this triangle here in blue, that's going to be 60 degrees there. And now, what I want to do I want to consider in yellow a triangle where that's parallel to the plane, and that's 30 degrees there. So this length here is opposite. There's my hypotenuse. So that length there is sine 30 times 20. Okay, so I'm just getting that angle in here of 30 degrees justified. All right, so now that we've got that angle, you can see this blue F force on my triangle over here on the left is this one here that I created in that little triangle there. So F on 20 opposite over hypotenuse is equal to sine 30. So F is equal to the 10 kilogram weight, the normal reaction, adjacent over hypotenuse, N is equal to 10 root 3 kilogram weight. All right, so it's just about creating that triangle with our forces and then using our trig knowledge to solve that. Righto.